this computer. So for today, I'm going to go ahead and share my screen. I know we haven't gotten up to this point yet. We're still working on getting up to this point. But today, the sole step is implement a system stack. So you can read through that later on, but I just wanted to go ahead and cover that the MVP for today is implement the system stack. I know everybody is a little bit behind, but I speak in terms of the MVP and the goals and whatnot, but I had a long conversation with Beach last night, and it was pretty easy to do because we've only got 3 people in here. Talk to him about where everyone was, what exactly was going on, how I felt things were going and all that. And, like I said, originally it's a difficult week. It gets easier as the steps move on. And Beach felt that overall, and he offered this up himself, this wasn't even anything that, I asked, but he thought everybody was in a good place overall, but just needed to keep pushing, not slow up. But he told me that kind of unofficially, he doesn't see MVP for the computer science section in terms of per day. Yes, it's got to be presented per day. Yes, it's being assessed in the system per day, but to him, it's more of a per week thing. So as long as you get to that goal, then the mission's been accomplished. As long as you've learned what there is to learn in the week, as long as you've gotten to where you're supposed to get to in the week, as long as you're able to get to the sprint and get through the sprint, then that's how he thinks of MVP. So, I'm still hopeful to see everybody at MVP, which is actually, I think, step 12 is the last step, and then you get into these stretches. But for today, we're going to go ahead. The entire GP revolves around stacks. So somebody, you can get on your mic or type in the channel, but today, because I don't have a whole lot of code, it's more of an interactive day. I'm going to ask questions, and I'll sit and wait. Even if you're not sure, answer with something at least, because that at least could help stimulate the conversation and keep the instruction moving. So somebody tell me what a stack is in real simple terms. What is a stack?
Stack is basically a way to handle data and store information. So it's like in terms of like a structure, it's first in, last out. So you push something onto the stack, and then you pop something off. So that would be, you can pop the last thing that was on the stack off, and you pop it down. So in this sense, in the way that we're using it to like keep track of where we were interrupted in interruptions, and then it gets put back into the processes afterwards.
Yeah,
I don't know if that makes any sense,
that's a great answer. Overall, a stack, and we're going to implement a stack in the most, because a CPU really implements a stack on the most basic of level. And we'll get into some things today. I don't know if they've talked to you in the past about Stack Overflow. Of course, you've heard the term. You probably know what it is, or at least have seen the implications of it. But we'll kind of visually go through what happens with the Stack Overflow. We'll talk about a Stack Underflow. If you've never heard of that, it's basically the opposite. We'll go over that as well. But yeah, it's a data structure. It is first in, last out. As you push onto it, they always told us it's like a stack of dishes, and every time you push onto it, you're adding a new dish to the stack. And when it's time to take something off, you got to pull the last dish that you put on before you can get to the next. So the exact opposite of a queue in terms of data structures. Anybody think of any reasons that come to mind why a stack is so useful as a data structure in a CPU, both maybe in terms of how we'll be using it here or in general in a program, in anything. What is so useful about a stack? I'll lead the question a little bit because it's a difficult question. Think in terms of function calls. Think in terms of function calls, and think in terms of things that might need to be stored for function calls. Anybody have any idea? I won't sit forever on this one, but if anyone has something they'd like to say, go ahead and go for it.
What was the question exactly again?
Why is the stack, in terms of being a data structure and the way it functions, why is that useful in a CPU? Specifically, what makes it really useful for function calls? Think about nested function calls.
Yeah, I think it's, I don't know. The one thing I think about is probably just accessibility, right? So if you have something that's already in a stack, this is how I'm thinking about it. It may not even be right. If you have something already in the stack that's already there presented, you just have to go there, pop things off or push things on, and you can just pop off 2 or 3 things and get to where you need to be, or push something on so it's just readily available. I don't know if that's like the answer or not, but that's how I think of it.
Well, what I was getting at specifically, it's a good answer, but what I was getting at, what I'm thinking of, to me, what the most important thing, or one of the most important things with a stack in terms of a CPU, and of course we're making a lot of function calls, think in terms of nested function calls and how they work, and local variables that have to be stored. So every time that we have another function call, we can just push all that in onto the stack. We know that the function calls go onto the stack, and that's why when, say, we talk about blowing up the stack with recursion, because we keep adding and we keep adding and we keep adding to the stack. And what happens when we keep adding to that stack? Remember, the stack starts at the top and moves down. Remember when we talked about the heap starting at the bottom, starting at the beginning, and move up? And when those collide, you've got a problem, or you potentially got a problem. We'll see a little bit more about that on a real basic level today. But what that allows you to do is, remember, as you nest function calls, you're dealing with the function that, the last function, the deepest nested function, the most recent function that's been called. So we're able to just keep adding to the stack all of those function calls, and then moving backwards as we work through, as we resolve those function calls. And, we're storing local variables, we're storing return information, all kinds of things. Does that make sense?
Yeah, that makes sense. Just like any function, like you're saying, if there's a function inside of that function or nested function, then if you actually follow the way the way that it moves through, will jump to that other function and complete everything in there before coming back to the original function it was in.
Exactly. So if you put it in a queue, that wouldn't work very well then, would it? Because you've got a first in, first out, and that doesn't follow how those nested function calls work. So yeah, there could be some real funky way or some really inefficient way that you could arrange a queue to work for you. But a stack, by its very nature, allows you to build upon those function calls and then go back and deconstruct everything and work back towards that original function call. Or in recursion, which is just basically nested function calls. You're just building as you branch down that tree of the recursion. And then as you start getting your returns and building back up, it's just moving back up the stack. So I don't want to spend too much time on that. It's just something I wanted to touch on. It's something Beej touched on with us a long time ago when we did this exact same this exact same module. And I think it's just an interesting point and one of those basic but important points of computer science that is worthy of talking about a little bit. So give me just a second. I'm going to pull something up on my other. Let's see. Everybody see my screen okay? Is it big enough for everybody, or can you, because the problem is I want this all to be able to show on my screen. So I think. Is that okay for everybody? Perfect. Good. Somebody speak up or type in the channel because I've got the video minimized.
Yeah,
now.
no, it's good.
Okay, cool. Okay, so we've kind of got a really basic implementation, just a graphic implementation of a stack here, just kind of in pseudocode. So what we've got here, starting at 0, we've got our memory. Remember, we allocated memory the other day. I think we allocated 128 bytes into the memory. For the purpose of this, I'm going to allocate 256 bytes. These right here are the memory addresses. They're in hexadecimal. Remember, FF in hexadecimal is 1515. So 15 times 1 times 15 times 16 to the 1, 255. The very bottom, 0, 0. So 0 times anything is 0. That's number 0. So, and we've skipped a lot of spaces here. The PC, remember we talked about that a lot the other day, is our counter, where our program is at. The instructions that we originally loaded, we hard-coded into the array, into the memory of our machine, that we later on went and unhard-coded it both here and working on that in the independent project to be able to accept an external source. Today we'll be working with this set of instructions, but it's our set of instructions. So this is just representative of our first instruction, our second, our third, our fourth, and here's our counter, our PC. So our counter is going to start at 0. Remember, and I'll just preempt anyone asking why I didn't start, and we talk about the stack starting at the other end of the memory, why I didn't start it up here. And these are just, the one thing else that I forgot to say, these 0 zeros, these are the addresses in memory. This is simply what is being stored in that address, and we've got these all initialized to 0 at this point. This, like I said, is just representative of code for our program, instructions for our program. These are our registers. Remember, our registers are a very limited set of memory that we can access. And register 7, by convention that they laid out in the spec, is the stack pointer. We are initializing the stack pointer at F4. Remember, these are holding a pointer, so this is pointing to an address, F4. That address holds 0. So this is the top of the stack right now. Is that clear to everybody? This is just some random information we're storing that we'll use later. This is the top of the stack where the stack initializes. The reason I left a little bit of space here is I want to be able to demonstrate a stack underflow. So I didn't start it up here, even though we could have, and it would have just done what it's going to do anyhow. But everybody clear on what I've got laid out here?
Yeah.
Okay, cool. So let us jump back. Today we will be in basically to implement a stack in our system. We've already got the memory there. We've already got these spaces in memory. So what do we probably have to, if we, the most basic sense of a stack, what would we need to do to our program to implement this stack? Don't overthink it. It's real damn simple. There's 2 things we got to do.
Well, to do this whole thing, we got to decrement and then push. I don't know if you're just looking for push or what.
Yeah, we just got to do a push and a pop. That's all we got to do. And it's real dang simple. If we go look at where is the spec? So if we look at the spec in the push, it's real simple. Push the value in the given register on the stack. So when we call the push, we're going to need the machine code for the push. Remember, we got this 8-bit binary number for the push. We're going to need the register. Only got 3 numbers here because remember, we've only got 8 registers and all we need is the first 3, 1, 2, and 4, and we can also have 0, so that's 0 through 7, so that covers the 8 registers. Push the value in the given register on the stack. So if we go back here, we've got these registers with some values stored in them. That's how we're going to be demonstrating this. So we're just going to take whatever value that we're given. First thing we're going to do is decrement the stack. Why are we decrementing the stack? That can seem a little bit not intuitive in the beginning. Why are we decrementing the stack? Somebody speak up. Why do we decrement it when we're adding to it?
Well, we're building down so that like when we go back in, we go back up like that. So yeah.
Exactly. It's so simple, but I've seen a lot of people really think about that, and I'm one of those people, and it was just really, really dang funny. You know, a guy that, you know, aced all these calculus and linear algebra classes and all this back in college, couldn't figure out at first in his head that we were decrementing because the stack starts up here. So when we're adding to it, we're going this way, and therefore decrementing because we're moving downwards. However, we've got this numbered. So yeah, that's all I was looking for there. So we're going to decrement the number so we have an empty space to be able to push this new value into. We got to copy the value in the register to the address pointed to by the stack pointer. So we've moved down to a new space in the stack. And we're just going to copy the value in that register. And that's all there is to it. And the opposite of that, pop, we'll just go ahead and look at that while we're in here as well. Somebody tell me what a pop does. Just in general, what's a pop do in JavaScript or Python or anything? What's a pop do?
It just removes the last element and gives it to you, returns it to you. So
yeah, that's exactly it. So that's great that you threw in it returns it to you. So it's just pop register. So all this is our code that we've got, our 8-bit binary code that tells us, hey, pop, and it gives us a register. So pop the value at the top of the stack into the given register. So it's going to give us a register in our instructions, like we see here, pop R2, pop R1. So that's why we've got addresses. R1, 32 is not a value. 12 is actually a value. Think of this as a value. This can be whatever we want to be, but because, and it kind of gets back to the point of a pointer is only, we can store whatever we want in these places in memory. A pointer is only a pointer because we're indicating it's a place in memory. I mean, we could easily go back and say, hey, it's going to be a value instead. It's going to be, 32 in this case refers to the address 32, which is in between 5 and EF. Gotcha, Frolin. Well, it's all being recorded in case you miss anything, if you can hear me. But thanks for letting us know. So 32 is actually an address in here, and then 32 theoretically contains 00 as well. 4A, that's a hexadecimal that's up in here somewhere as well. This is an actual value. And actually, the way I have this set up, I was lying to you. This is a value as well because we're going to push R1. So these are both. This is a decimal number 32. This is a decimal number 12. This is an address, a hex address 4A. So go back here. we're just going to pop the value at the top of the stack into the given register, copy the value from the address pointed to by SP to the given register, and increment the stack pointer. So we're just going to copy that value. Why are we copying that value? Because we're going to return it. So if we're going to get rid of it, we're going to copy it, just like we did when we implemented the data structure. When we pop it, we need to make a copy of it first before we pop it so that we can return it, store it in a variable so we can return it, if you remember that. And that's all there is to it. It's a fairly simple implementation in our machine, and it's actually once you get past some of the initial problems of getting the run going and getting the idea down of implementing all this functionality, that's all there is to implementing a stack, the basics of it. So we go back to our code here. We've explained this little faux data structure that we've got set up. I've explained that these are our registers. The stack pointer, just by convention, is holding the pointer, the address, so it's holding the address F4 and the value 0. This is where the stack initializes, and we've just got some values in here so we can perform some actions, because it's that our spec is asking us to perform these actions on the register. So we've got these 5 actions that we're going to do. Everybody clear up to this point on everything that we've gone over in the spec, everything we've gone over here, how I've got this laid out? If you don't speak up, I'm going to assume you're clear on it. I just wanted to check in real quick.
Yeah, clear.
Cool. So our first instruction says push R0. So we're going to say, okay, we've got the value 12 in R0. When we push, what's the first thing that we had to do? Somebody tell me. What's the first thing we do in a push?
We had to decrement first.
Yeah. The decrement, so we're going to take this. We're going to decrement the stack pointer. So now we're here at F3. I'm going to take this value 12. We're going to copy it to here. That's all there is to it. Now we say push R1. We're going to do the same thing. Move the stack pointer. We're going to copy the value 32 into it. Then pop R2. Somebody tell me now what we're going to do when we pop R2. Tell me what happens with the stack pointer, what happens with our values and where they're being held and stored, and which way everything's going to move. Give it the best shot. Pop R2.
So we're just going to get the value there and put it in our register 2, I think. And then
the value where? You said the value there. What value?
F2.
Yep. And we had a pointer in there. Now we're just going to override it with the value. And then what are we going to do after that?
Then we got to increment it.
Yep. And what happens to this right here? What happens in any language that we've dealt with this value right here? Nothing. Absolutely nothing. You could go back in there and clean up every value, but that takes away from efficiency. So unless you have a specific reason to do so, it just stays there. And this is a reason you always initialize variables. If you don't initialize a variable, we talk about those garbage values that sometimes local variables can hold. Because remember, the local variables are on the stack. As we're messing around with this stack, say we initialize a new local variable and it happens to get this space in memory, that local variable points to F2 now. Let's say theoretically, what value is going to be in that local variable if we don't initialize it? 32 is going to be in there, right? Another little side note that doesn't really have anything to do with today, but does that make sense to everybody?
I think so. So I'm just trying to. So the 32 stays in register 2, and that's because we popped 2 R2 is what basically what.
That is specific to, that is very specific to these specs. Yeah, it's just saying copy it to the register, so that's what we're doing. But it stays in memory right here because we just made a copy of it and then we just decrement it. But the problem is, if we want to access it again, our stack pointer's here, and it's, we know where register 2 is, so if we want to access this, if we need to access this, it's easier if we've got a copy of it down here than trying to go back and move the pointer or increment things up. We just know, hey, it's sitting in R2. Does that make sense? But that's more specific to our machine. My take home really of all this was that this value persists. This value does not become 0, 0. This value does not become null. This value does not become undefined. This value persists. Kind of also the real basics of a lot of time when you delete things, you don't really delete it right away. But that gets a lot more complex. But in the most basic sense of a stack, and like I was saying, remember that local variables go onto the stack during these function calls. And if we don't initialize those local variables, if we initialize that local variable to 0, well, then we got 0 again. But if we don't, we can have a garbage value in there, which might not really matter, but not the cleanest, and it could matter. Like I said, a little bit of a side point, but I just wanted to point that out. So we popped R2. Now we're going to pop R1. So we got 12. We're going to go to R1 and store 12 there. Oh, and we popped, excuse me, I did. So what are we going to do with the pointer now?
Move it up to F4.
Yeah. And now we've got the pointer at F4. And we've got R1, 12. We're at F4. Where are we at now? Remember F4? Where are we at? We're at the beginning of the stack, right? That makes sense? We're at the beginning of the stack. There is nothing that constrains us from popping on an empty stack. Yes, programming languages, high-level programming languages have things in place to keep you from doing that. But in its most basic sense, a CPU, it just does what you tell it to do. So, you know, you might get mad at the computer, dang, you just let me blow up the stack, and the computer, if it could talk, would tell you, no, I just did what you told me to do. So there's absolutely no reason we can't pop an empty stack. So if we pop R1 again, what happens?
We would get 0, 0 in the R1.
Mm-hmm. And what happens to the stack pointer?
Yeah. So we just keep going up. That's not good.
Right. So now we have a stack underflow. If you've never heard that term, it's basically we have sometimes it's not intuitive. Well, how the hell does that happen? Because the stack only starts here. So, you know, we can, if we go out of bounds, we know, well, you can go out of bounds the opposite way as well. And it's in physical memory. So now we're pointing at F5. And then if we keep doing that, we're going to point at F6 and F7 and F8. And what happens when we get all the way to FF? What happens if we pop that again? If you haven't read it, or if you just don't happen to know this, it's not real intuitive. But if you pop here, it's just going to loop back around in this 256 byte system, because if you add one here, you actually end up back here. And if you subtract one from here, you actually end up back over here in hexadecimal. But that's a point that we don't need to dive into. If you want to know more about it, think about it a little bit more, go look it up, or we can chat about it one-on-one later. But basically just know that for practical purposes, it's gonna roll back around to here. Now let's say when it rolls back around, let's say our instructions have been working. PC's here. We still have our instruction here. So not a problem. So we can just keep popping, and all we're going to keep doing is just looping around, storing the value in R1. If we just keep saying pop R1, more or less, no harm, no foul, but you got a really screwed up situation going on. Here comes my other question though. What happens if we just keep pushing onto the stack? Remember what happens when we push? We store that value, we take the value from the register, and let's just say we created an endless loop that said push R2. We're going to keep pushing R2. What would happen? Somebody speak up.
I feel like we would crash because we are overriding like all of the other registers, right?
Well, what's going to happen is we keep pushing. You're just going to keep pushing. If you keep pushing R2, we're just going to keep. Let's say we were at F4 and we just kept doing it. So then we push R2. We've got 32, and we've got 32, 32, 32, 32. We're going to leave these zeros. And what happens remember, we've got all zeros in between there, and we're overriding them with the 32. Think in terms of the PC as the machine is running its instructions.
Yeah, I guess so. It would eventually just hit like 32, right? And that would just be, and that's all it would ever hit would be 32, 32.
Yeah,
so,
and let's just for an example's sake, because I realized what I was trying to do isn't going to work. Let's say we kept pushing. Let's say we just kept pushing on zeros at this point. So we got to here and we pushed to 0, and then we got to here and we pushed to 0. And the computer's here. So what happens? So now we pushed a bunch of 32s. Just doesn't matter. I was just using that register. And then say we just said push R1 a bunch of times, and we kept pushing R1, and now we've got a bunch of zeros pushed onto here. We're at this instruction. Now the PC increments up to 0. Now if we go to our spec and we actually look, because remember this is binary that it's looking at. So that machine's going to say 0, and it's actually going to hit this. It stands for no operation, do nothing. So it's just going to skip forward. But the problem we run into in our little machine, what happens wherever the heck it does it, that we hit 32. I can tell you there is nothing, even if we're converting this, let's just say we're converting this decimal to binary, there is nothing that is binary code for 32 in our spec. And like someone said earlier, we're going to crash. I know this is kind of a simplistic little representation, but does anyone have any questions over what I did? Does this help not only in terms of our machine, but just explain a little bit, if you didn't already know, what's going on with a push, with a pop, with the stack, with a stack overflow, with stack underflow, if you've never heard of it before, why things can crash, why there's a problem when, everything that's going on with our program here that's moving upwards, it was in a nice loop. It was contained within a nice loop here. And then eventually, remember, we had a halt, but it broke out of this loop when it hit this zero. Oh God, we overrode our halt and we hit this zero. We kept pushing these zeros on, but hey, no problem. There's a zero. We've got that covered. We've got a zero in our instructions, but our silly selves kept pushing this 32 on that eventually now we broke out of the loop. So the computer goes through all the zeros and hits this first 32 and we crash.
So do we need to set like limits for the stack then?
In your machine, no, you don't have to. In reality, under the hood, yes, that's exactly what's going on, is that there are programming languages have protections to some degree or another in place to try to prevent things like this from happening. But here, in the most basic sense, in the way that we're implementing it, both here and in your code, this is why we've got to be careful. And this is why things like the C language, this is why when we get down to the nuts and bolts, the zeros and the ones literally of an operating system, of a CPU, why having so much liberty can cause so many problems so quickly. Does that make sense?
Yeah.
Anybody have any questions about what I've demoed here? Just a basic demo. There's not too much to think into it of it, but in doing the demo, I covered first what we're doing today with the stack. I covered what is in the spec for the push the pop, and we kind of got the no op thrown in there as we demoed what can happen here. And I just demonstrated how we're allowed to pop an empty stack, or what happens if you keep pushing onto the stack or keep making recursive function calls in a much more complex sense and adding to a stack and adding chunks to the stack and adding chunks to the stack, and boom, suddenly it hits the instructions, the program that's running, that's moving this way, suddenly makes that collision that we've talked about. And there you've got your stack overflow. So enough on that. This is the code exactly as I gave it to you yesterday that we've got. So of course, we're not going to go back through here and add every last piece of code, but nothing has changed in this code whatsoever. So we talked about it earlier and we said, what do we need to do today to implement this stack? We've already got our memory sitting right here. Now our memory is 128 here. It's just a random number that we put into. That doesn't matter. We don't need the 256, but we'll just say for all practical purposes that we're going to start it at 128 here. There's no rhyme or reason to it. It's just what I did. So all we got to do is implement the push and the pop. We got the memory. We've got all the pointers already where we're at. We got to add a stack pointer. Add a push, add a pop, maybe define something here. And then we've got this meta program here. It's just going to say a print John, and then we start saving numbers and registers and pushing and saving numbers and registers and push and pop and whatnot. And you can follow through this if you want on your own later on. But all we're doing is pushing 65 and 99 onto the stack after we save them by giving them those registers. And then we're going to pop 99 and 65 off the stack and print it. And the specifics of these directions don't matter. This is basically just our test. But this is the code that we're going to access in the command line like we're able to do it now. We don't have to have this hard coded in. We can go copy this all into memory and do like we did in the very beginning, but we're beyond that now. So probably want to define something here. So we'll say define push, and we'll give it an 8. Define pop. give it a 9. Anything else up here anybody can think that we need to do?
Not at the top there, but where's our, where are we running this? Just like after?
What do you mean by where are we running this?
So we're running it within this code that already exists, right? Within the, so are we running it like after all of this stuff happens in the main, or?
Yeah. All we're going to do later on, this is just the file that we're going to run. Okay.
Yeah.
So all we're going to do once we implement this push and pop that we just defined, we're going to implement it down in the switch. Remember, all that we're doing here, this is all just loading the memory. It's grabbing that file. We initialize a few variables. We grab that file, and just like we did over here, we're just loading all this into memory. Loading this program into the memory since it's not hard-coded. So remember right here, we have our int main, and we're taking in, remember we talked about this, the argument count. We've got our arguments here that we're loading in. We've got our running for the while loop. We've got our current index. We're just checking our arguments to make sure we've got 2 arguments to make sure that we've got whatever file we're going to run. Got this temporary little storage here going on for reading in the file. We access the file, doing the file, opening the file up, making sure there's something in the file here with this check. And then we're just going through the file and reading the file like we talked about the other day. We're just using this. And remember right here, memory at address plus plus equals value. So we're getting the value. Remember this string to unsigned long. We're getting that value, not binaries here. We're just using unsigned longs here in this basic program, but we're taking that, turning it into an unsigned long.
What does the 10 stimp mean again in there?
That is the base. So because it's decimal that we're dealing with here, it's 10. In your program, it would be 2 because we're dealing with binary. You could put, that's just the base. That's where it interrupts. Remember the end pointer. This is just where it's storing it to temporarily. We're just making a check to make sure we didn't hit that end pointer and doing nothing. We're not printing it like we did for an example yesterday. But the big thing is for each line, we're grabbing that value that we've converted from that string. Remember, this is all a string. We got to convert string to long. And we're just grabbing that value, storing it in memory. So this is all this all right here is just what we've already covered. It's just being able to take these files and run these files like we were doing the other day. And remember, all of these, yeah, it's all written out, but there's all we're doing is we're pulling 1, 5, 65, 2, 8, 2, 5, 99, 2, 8, 2. In your program, we're pulling 8-bit binaries. Does that make sense? So it's just that our string to long is just grabbing these, turning them into a long unsigned or a long unsigned, and adding them to the memory. Same as right here, the memory that's just building up, and that memory starts here. Remember, our pointer, our current address, it runs our program. Is that clear?
Yeah.
Cool. Everybody else good?
Yes, sir.
Cool. So one thing I'm going to do here after we close, just because, is we're going to say registers at 7 because that is the register that we are told in our spec to use. And equals, we'll say 120 because we've got 128 that we've allocated for our memory here. So we'll start it at space 120, because remember, it's going to move this way. It's going to move from the top towards the bottom while the program's moving from the bottom to the top. That's all we do there. Just initializing register 7. This is the stack pointer, is all this is. Then got our variables that we initialized the other day, and then our while loop. Remember, this is just grabbing the command, looking at our place in memory that our pointer is at, looking at where the command is pointing here. Should ideally be pointing back down here. I'm just using this as an example over here. This really has nothing to do with the program, but I'm just kind of using it as a graphic example. So this is just grabbing that current index in the memory, getting the value of it and calling it command, and then we're going into the switch statement for that command, and we're looking in the switch. Of course, we've got these definitions up here that turn them into numbers, and it's looking, what do I do? And when we look over here, hey, I've got a 1. So what are we going to do for 1? What does 1 say to do? Oh, 1 is print John. So we're going to print John. So when our switch is down to print John, it prints John. So I'll go ahead and preempt this, that there's absolutely nothing else that we need to do in the code but implement, push, and pop. And we'll just do that right here at the top. So before we do that, I'm going to give everybody a 5-minute break. It is 13:30 my time, so at 35 minutes past the hour, let's meet back, okay?
Sounds good.
All right, everybody take a quick break, grab some coffee, do what you got to do. 5 minutes and we'll implement this and see how it works. Cool, cool. Everybody back?
Yep, yep.
Yeah, I think Frolin's still having internet issues. Jeez. Okay. So we've gotten to the point in our program that all we've got to do is add a push and a pop. So we will say case push. Remember when we're pushing, what's the first thing we need to do?
Decrement first.
Yep. So we will just say registers 7 because we using that's our stack pointer. We're decrementing. And then remember in our instructions how they work. Let's go to here. Remember, we get a push, which is number 8 right here. And then we're going to push, it's telling us what register to register to. What's in register 2. So what would we need to do? Next, say we'll save it to regnum. Remember, our memory right now is pointing at the command. So what do we need to do to get the register number?
Need to add 1.
Yeah. Take the current index. Remember, the current index is keeping track of where we're at, and we just add 1. And then now we know where we're at. We need the value at that register. Val, these are just, we just initialize these up here. So the value at that register will be what?
Isn't
Go ask.
I'm just curious, isn't that first line already returning a value? Or is it returning?
You mean the line where we're pointing at in memory right now with the current index?
Okay, I see what's going on. Okay.
Remember, so we're pointing, we're here in the instructions right now. Boom, we've jumped forward from this last one. It told us we knew how many we needed to increment, so we're at 8 right now. And now we're in the while loop. We've got this command. But we need to get this 2 because that's the register. That value in that register is what we need to push. So to get to this, we need to say registers at regnum, and we got that regnum by saying memory at the current index plus 1. The current index is pointing at the instruction, so we need to add 1 in this case to get to that reg number. And then we need to just say registers at that reg number to get the actual value, whatever the heck's in there, from there. That makes sense?
Yeah, that makes sense.
And then we're going to go into the memory now. And remember, we've decremented the memory. So we're at the place in the memory we need to be. So we just say memory at register 7 because we've decremented the memory. This register 7 is storing this value right here. So we've decremented this. We're ready to push. It just equals to the value. And then we know that since we have 2 instructions here, That's all there is to it. The code here is a little convoluted looking the first time you look at it, but all we're doing is what we talked about in the spec. We got our counter, we decrement our counter, we access the register number by moving one space forward in memory, one space past the command that we're at to get that register number. We then access what value is at that address by just using array notation inside the registers to get the value. And then in the memory that we've already decremented, the new spot, the next spot in the stack, we just put that value on there, and then we just increment the index up to get to our next command. Could be another push, could be a pop, could be a halt. Any questions? So for pop's a little bit different. What would be the first thing we needed to do with a pop?
First thing we need to get is to pop off the value. I guess you need to, because we just got the instruction, right? So we need to
think about in terms of how a pop worked, and we're still dealing with a register number. We don't have to deal with the stack pointer yet, because we're not, remember we decremented first, but the first thing we got to do is remember we're saving that value somewhere to theoretically return it later. So the temporary variable reg num. We need to get the register that we're going to save it to, don't we? Remember? When we pop, we first save the value that's in memory.
So it's the same as that line in push, correct? Or we?
It's the same. No, yeah, you got it. It's the same exact line. We're just getting that reg number. So now we know where we need to save it to. That's all there is. And now that we got the register number out of memory, then we need to go into the registers at that reg num. And save the value that we're about. Remember, the stack pointer is now still pointing to what we're going to pop. So we're just going to save that value to that reg num. We get that reg num, then we save the value to that reg num. Then what do we need to do? Don't overthink it.
We just need to, well, we need to increment the register.
That's exactly what we need to do. That's all we got to do. And that's all there is. So, the terminal up, make sure and save this. We're in the desktop, which is where this is. So we will say GCC wall extra output to arch3, arch3.c. The heck is this? I didn't put an underscore. Where did I do that? line 78. Then we'll say arch3, and our file was named stack.meta. And we've got John 99 and 65, which follows exactly what we expected here. Anybody have any questions?
Maybe could you write? Are you gonna put this in Slack?
Yeah, I'm gonna put all this in Slack. I will put that right now.
Do you mind actually putting some comments beside maybe just the operations in push and pop?
Sure. Like, what did you have in mind? Like, you mean right here in here?
Yeah, like those 3 lines specifically: 65, 66, 67,
Oh,
and then
sure.
and then also 73 and 74.
Yeah, once we jump off the video, I will comment it real quick and put it into Slack. No problem. I can drop the meta file in there if you want. Like I said, I don't really know why anyone would. You shouldn't really be playing around with this, but this definitely is good reference for the code itself. Is good reference for what we're doing in the independent project. But yeah, I'd be happy to do that. Anybody else? Anything? Both of y'all stick around because I'm going to DM y'all like right after I'm done commenting this, and we're going to meet for a quick one-on-one, and we'll just chat about where you're at, quick and painless. And then you have some time before lunch, during lunch, if you want to work. And depending on where you're at, we might meet up again for a one-on-one in the afternoon, not the daily one-on-one, but it'll serve that purpose. But, you know, if we need to have some time, you know, some one-on-one time to help you work through some blockers, we can go from there. But we'll figure that out when we meet. So if nobody has anything else, I'm going to end this. I will start uploading this to YouTube. I will get the code commented like you asked for and drop that into Slack. And I'll contact each of y'all to chat real quick. Sound good?
Great, thanks.
Hey, no problem. Thank you.